Chapter 14, Section 4 is on center of mass and moments of inertia. Our objectives are to find the mass and center of mass of a planar lamina using double integrals, and to find moments of inertia using double integrals. This picture shows a shaded region R. We can find the mass of a lamina corresponding to that shaded region. If it has a constant density rho, then the mass of that lamina can be found by the following. Mass is equal to the rho, which is the density, times area. And you can find the area of the region by setting up a double integral where R is the region, and you would use that region to define the bounds of integration. And dA is your differential area. Now dA could be either dy dx or dx dy if you have functions in terms of x and y. So this, when you multiply, you can distribute that density to get the double integral of R of the density times the differential area. Now suppose the density varies. Then this is the definition of a mass of a planar lamina with variable density. If rho is a continuous density function of the lamina corresponding to a plane region R, then the mass of the lamina is given by m equals the double integral over the region R of that density function rho in terms of x and y and your differential area. Here's an example of finding the mass of a planar lamina. Find the mass of the triangular lamina with vertices at 0, 0, 0, 3, and 2, 3, given that the density at any point on the lamina is defined by this function, rho of xy equals 2x plus y. So you can actually determine the density at any point along in the lamina by indicating the location x and y and plugging it into the formula. In this case, if you see, look closely, the shading of the lamina appears to be darker at the top right of the function of the graph. And that means as the x and y increase, the density is also going to increase. The closer you get to 0, the density is closer to 0. So we need to determine the region and use a double integral where we can multiply the mass times the differential area to get the total, get the density times the differential area to get the mass. So we need to find equations that we can use for the upper and lower bounds for x and y. If you connect the point 0, 0 with the point 2, 3, you'll know that the slope of that is 2/3. So the slope of that is up 3 over 2. So we can say y is equal to 2/3 x, or you can say x is equal to 2/3 y. And the line that connects this vertex with this vertex is this vertex with this vertex is the line y equals 3. So again, these are the boundaries that we'll be using in our integral. X equals 0, that's the vertical line that is on the left side of that region. The line y equals 3 is the top portion of the region. The line y equals 3x over 2, or you can solve this for x to get x equals 2y over 3. And those are the boundaries. So the mass of the lamina is the density function, which was defined to be 2x plus y times the differential area. And we can determine the bounds of integration, where the y goes from 0 to 3 as the x goes from 0 to 2y over 3 of the quantity 2x plus y dx dy. When you integrate the inside, you would treat x as a variable and y as a constant. Antiderivative of 2x plus y is x squared plus xy. And you're going to evaluate this at the upper bound. You're going to be replacing x with 2y over 3, and then replacing x with 0, and simplify the result. When you simplify, you get the integral 10/9 the integral from 0 to 3 of y squared dy. And you can integrate that and simplify your answer to get 10. So the mass of the lamina depicted on the previous slide is equal to 10. Now we can use mass to find the moments of mass as well as the center of mass. The notation that we have here is m with a subscript x. That's the moment of mass about the x-axis, as well as m sub y, which is the moment of mass about the y-axis. And that is found by taking the mass and multiplying by, in this case, m sub x is found by taking the mass and multiplying the distance from the x-axis, which is your y sub I. And then the m sub y is your mass times your distance from the y-axis, which is your x sub I. So the moments of mx and my used in determining the center of mass of lamina are sometimes called the first moments about the x and the y-axis. In each case, the moment is the product of the mass times the distance. So the moment about the x-axis is the distance to the x-axis times the mass. And you can set up a double integral to find that moment. And the moment about the y-axis is equal to the distance from the y-axis, which is x, times the mass. And again, the mass is the density times the area. So you would be setting up 3 double integrals altogether, one for mass, one for the moment about the x-axis, and one for the moment about the y-axis. And those are going to be used to find your center of mass. So this slide shows the formulas for the moments of mass with respect to the x and the y-axis, m sub x. This double integral has a y in it, and m sub y, this double integral has an x in it. And both of them have the density times the area. Now if m is the mass of the lamina, then that center of mass can be found by taking the moment with respect to the y-axis dividing by the mass, and the moment with respect to the x-axis and dividing by the mass, and you get a point in the plane. That's your center of mass. If R represents this simple plane region rather than a lamina, then this point is called the centroid of the region. It's like your balancing point. In this example, we are going to find the center of mass of the lamina corresponding to the parabolic region, where 0 is less than or equal to y, which is less than or equal to 4 minus x squared, where the density at the point xy is proportional to the distance between xy and the x-axis. So let's look first at the region that's given by this inequality. Well, y equals 0, that's your lower bound. Y equals 4 minus x squared, that's your parabola here. So it's bounded on the bottom by the line y equals 0, and it's bounded on top by the line, or the curve, y equals 4 minus x squared. And since we're given that the density at a point is proportional to the distance between that point and the x-axis, we can set up an equation here where density equal is proportional to the distance from the x-axis, and that distance is y. So we have the density rho of xy equals k times y, where k is that constant of proportionality. Now, because the lamina is symmetric with respect to the y-axis, and the density is equal to k times y, that center of mass is going to lie right on the y-axis. And going back to the side here, the density is proportional to the distance between the point and the x-axis. So, and since the left half of this is the reflection of the right half, that center of mass is going to be somewhere on that y-axis. Okay, so we can say that the x bar, the first part of the center of mass, the first coordinate is 0. To find y bar, we need to find the mass of the lamina, and remember mass is the density times that differential area, and k times y is your density, and the differential area is dy dx. Your lower bound for y is 0, and your upper bound for y is 4 minus x squared. Your left x bound is -2, and the right x bound is +2. When you integrate the inside with respect to y, you get y squared over 2, and since k is a constant, you can bring that out in front with the 1/2 when you integrate. And then you evaluate the y at the upper bound and the lower bound and simplify your result. And then you are left with a single definite integral. And you can take the antiderivative and substitute in the upper bounds and the lower bounds and simplify the result to get the total mass of 256 K over 15. Now that's the mass of the lamina. To find the center of mass, we first find the mass, and now we want to find the moment about the x-axis. And when we set up the integral for the moment about the x-axis, it's going to look very similar to this. The only thing we're going to do is change this part here because we want the distance from the x-axis to be included in our double integral. Okay, so the moment of mass about the x-axis is the same bounds of integration that you use to find mass. It's the distance from the x-axis, which is y, times the density times the differential area. So if you notice, going back to the previous one, this double integral was essentially the same, except now we're adding this y. So when we integrate the inside with respect to y, this is k times y squared, and we integrate that to get y cubed over 3, and that k along with the 1/3 comes out in front. You evaluate at the upper bound and the lower bound and simplify your result to get a single integral, and then you work it out to find that the moment about the x-axis is 4096 K divided by 105. Now you're going to use this answer along with the mass. You need to divide this by the mass to get the center of mass. So the y bar is the moment about the x-axis, or with respect to the x-axis, divided by the mass. And those k's will end up dividing out and simplify to 16 over 7. The center of mass of that planar lamina is 0, 16 over 7.